So we're going to now show you something we can do with the dot product. Something that drops out neatly to work towards what the point of it is, why it's worth learning at all. And what we're going to do here is convert these vectors into polar form and then see how the dot product rattles through nicely. So the first vector has a radius and the x value will be the cosine of some angle and the y will be the sine of the same angle, r1. So vector 1 has radius 1 and theta 1. And you've seen polar coordinates before, so that conversion shouldn't be too alarming. And we'll do the same with vector 2. And we'll apply the same rule we learned last time about vector products, scalar products. We get r1, r2, cosine of theta 1, cosine theta 2, and we get r1, r2, sine of theta 1, sine of theta 2. r1, r2 is a common factor of cosine theta 1, cosine theta 2, plus sine the first angle, sine of the second angle, closing the bracket. Now, if you've remembered your trig identities, you will recognize this. This is actually the difference. It's the cosine of the difference of the angles. It's the cosine sum, but it should be a subtract here, so it's been the sign changed. So we get r1, r2, cosine of the difference between the angles. So geometrically, r1 is the size of the first vector, r2 is the size of the second, and then the difference between the angles is in fact the angle between them. Okay, so if we have vector A dotted with vector B, as well as getting our formula from last time, we also get the size of A multiplied by the size of B multiplied by the cosine of the angle in between them. Now, this turns out to be a very useful form of the dot product. The fact that it links to this gives us all kinds of helpful things we can work out. As you can imagine, knowing the angle between two vectors is very, very useful. I've done the proof here in 2 dimensions because it's something we can do on a single-sided paper. If you have the inclination and the algebraic chops, you can do the same thing in 3D and then do some transformations to the function you get to rotate things to line up, and it all comes out the same. And then once you've got that, you can repeat the 4, 5, 6. And if you're feeling really brave, there's a generality proof as well. But this is true in all dimensions, just like the dot product is normally. Okay. And this is a scalar, it's a single number. So it fits all out the properties from before. I hope that makes some kind of sense.